Welcome to homework.
Hello, my name is Margaret, and today I'm going to be helping you with Chapter 18, problem number 15 out of the Zumdahl book, which states, if the cell potential is proportional to work and the standard reduction potential for the hydrogen ion is 0, does this mean that the reduction of the hydrogen ion requires no work? So I'm going to do my best to help explain this to you guys. It's going to be a little challenging because there's really not, a problem to be solved. It's going to be a lot of explanation, but I will do my best to try and write out as much as I can in terms of explaining things. One particular section that I know I'm going to reference a lot is in the textbook, and so it is obviously chapter 18. It's section 18.3 at the very beginning. It's on page 714 of the textbook, and if you're using the PDF, it's page 892. The second paragraph says the work that can be accomplished when electrons are transferred through a wire depends on the push, the thermodynamic driving force, behind electrons. This driving force, the EMF, is defined in terms of a potential difference in volts between 2 points in the circuit. So let's write that down. So work work that can be accomplished when electrons are transferred is based on EMF or potential between 2 points in a circuit. I'm going to go back and make sure that I did not screw that up too much. Okay. So the next line it says is recall that a volt, which is that potential difference, represents a joule of work per coulomb of charge transferred. That's a lot of information. So I am going to write that down. So the EMF, which we'll write that down, potential difference, EMF is equal to, beneath I'm going to write in parentheses that value's in volts, is equal to work in joules divided by charge in coulombs. So, and then it says, thus 1 joule of work is produced or required, depending on direction, when 1 coulomb charge is transferred between 2 points in the circuit that differ by a potential of 1 volt. And again, that's a lot of information. And essentially what they're just saying in that sentence is a matter of standardization. And then it says in this book, the work is viewed from the point of view of the system. And so thus work flowing out is indicated by a minus sign. And when a cell produces a current, the cell potential is positive, and the current can be used to do work. So something else that is required is that current is required to do work. And then something else they say in that section is that cell potential and work have opposite signs. And so the other thing that they say is that work what is it that they say? Yes, okay, so work flowing out of the system is negative. And that's for this book, and that's why this is the case. Okay, the cell potential is negative. So, and that's when we start to see this equation. That is not the right symbol. Charge, which is Q. Now, something else that I think is useful is that if I'm remembering correctly, Q, which is charge, is equal to current times time. And because the reason for this is that and I'm just going to work this out real quickly because charge is in coulombs and current is a coulomb per second and time is in seconds, and so these cancel, and so yes, okay, that is correct. So that is everything I think we want for now. So something that we want to also remember, okay, is that all potential is relative. And this is not necessarily something that's covered in the textbook. Okay, this is me talking to you as somebody who does this for a living. Okay, the only time potential is not relative is if it is measured, unless measured in a vacuum. Okay, and that is why the hydrogen ion reaction has a potential of 0 volts. Is because we said, well, doing all electrochemistry in a vacuum sounds awful. And so we said that we're going to take a reaction that we know is really stable. And we don't mean stable in terms of what a lot of people think when we talk about something being chemically stable, meaning that it's nice and consistent. It's not going to be something that's volatile or reactive. We mean that the potential is consistently going to be the same, regardless of how long that reaction is going on. And that was the hydrogen ion reaction at the time. We knew that it was consistently the potential that we were measuring it inside the vacuum, and it was consistently the same potential when measured against other reactions. And so we decided that this was going to be our zero when we decided to measure other things. And so that is why it's our zero. There are other reactions out there that are that consistent and that we use to measure other things against. One of them is called silver chloride. And the other one is the electrode itself is called a standard Calomel electrode, or an SCE. And it's some kind of mercury. It's a mercury solid, mercury plus electrode, and that's why a lot of people don't like to use it. It's because it's got mercury in it, and mercury 1 in particular is fairly challenging to work with, and by challenging I mean kind of dangerous. So why did I take this detour? Well, and this is why I said that this one in particular is challenging, is because essentially what we've seen here is that there are a lot of variables that come into play when we're talking about something like work. So the other thing that's in particular is that when we're talking about the potentials for these reactions, and when we even talk about the potentials inside the standard reduction potential table, those are only true for the regular potential of, a particular pressure of the Earth at 25 degrees Celsius. And if you vary the pressure or the temperature, then you are going to change the potential. If you decide to go into Death Valley in the southwest of the United States and start doing electrochemistry, those potentials are going to change because it is so much hotter there than it is 25 degrees Celsius. And so if you don't meet one of the requirements that they've outlined here for work, then you're not going to do work. So is it possible to do work with the hydrogen electrode? Probably not. But it's also unlikely for you to do work with most of the reactions that are around, and that is because current is required to do work. The amount of current that is required to do work is a very large amount, and most of the reactions that we do in chemistry generate very, very small amounts of current. We're talking an amp or lower, and we need, massive amounts of amps in order to do appreciable amounts of work. And so that is why and that's why I thought this problem was fairly tricky, is because no, it's not going to do work, but not because it's special, not because not because its potential is zero. It's because it's unlikely for a lot of things to do work at all at the concentrations and the potentials that we have. If it were easy to do work with any old type of reaction, then there wouldn't be this ginormous industry of people developing batteries and clean energy. It's simply not easy to get chemical reactions that are cheap and easy to and clean in order to